Just give me a second. I need the charger.
Of course.
Oh.
Dajun Zhang is going to be chairing this session. So all I'm doing is making sure that the housekeeping rules are understood and everything is set up right.
Mm-hmm.
So let me just give a message to all the participants. As I just said, in case you didn't hear it earlier, please keep your microphones muted while the talk is going on. You can put your questions on the chat or raise your hand. And at the end of the talk, if you'd like to ask a question face-to-face, you can unmute yourself and show your video. But for now, I'm going to hand over to Professor Zhang to chair the talk. Thank you.
Thank you, Nalini. Are you ready, Yangdi?
Yes.
Okay, so I'm Dajun Zhang from Shanghai University, and I will chair this session. Today, the speaker is a young professor from University of Science and Technology of China, Professor Di Yang. He will talk about on tau functions of the Kdb hierarchy. Can you start?
Yes.
Okay.
Yeah. Thank you very much. First, I would like to thank the organizers for the invitation. So the topic today is about tau functions. So in particular, it's for Kdb hierarchy. So this topic is I would say it's quite typical of interval systems. So we know that the Kdb Kortewich-de Vries hierarchy is one of the most important and also the first important example that we study in interval systems. So it's I believe everybody is familiar. So I will start with maybe a brief recall of the Kdb hierarchy, and then we move to the main consideration about tau functions. So yeah. So the work is joined with Marco Bettola, Boris Dubrovin, and Dan Zagier. So the Kdb equation, it was discovered in the study of shallow water waves. This is an example of integrable partial differential equations. It is nonlinear, and of course, I mean, if it's linear, we usually consider as integrable. So so it's a nonlinear equation. And integrability means you can find the infinite many conservation laws, or you can find infinite many infinitesimal symmetries. So and in particular, we can give all the or say a large family of commuting of the symmetries of this equation, which is the Kdb hierarchy. Of course, you do any linear combination of this symmetries, which is this. Let me yeah. So this is the infinitesimal symmetries for the Kdb equation. So it's in the Flux form, and I won't say that any linear combination of this symmetries, you get another infinitesimal symmetry. So there are many symmetries of the Kdb equation, and also all these infinitesimal symmetries, they commute pairwise. So they are the symmetries itself. Each symmetry itself is the symmetry of all the other symmetries. So this is the Kdb hierarchy, and in particular, all these infinitesimal symmetries, they are, each of them are evolution PDEs, and so and together they are called the Kdb hierarchy. And this hierarchy, the point is that it can be solved together, in the sense that the initial value problem of this infinite many PDEs, they have common solutions. So it's because this pairwise commutativity. So this is what we will just say here. And so in particular, if k equals 0, you get a trivial symmetry, which is du dt 0 is just du dx. So we because of this, we identify this t0 variable with x. Okay, so it's our space x is identified with t0. So this pairwise commutativity, as I just explained, it implies we can solve the equation together. And so the partial goal of our study is to solve the initial value problem of the Kdb hierarchy. So the problem is to solve the equation of the whole family of the equation, not just one equation. So because of this, we have infinite many equations to solve. And so the initial value problem is that at all time equals 0, we give the initial data. So for us, we will do arbitrary initial data. So let V be any ring which is closed under differentiation in X. And for arbitrary initial value Fx, so we can consider this is the initial condition, and to solve the problem is to solve the Kdb hierarchy. So of course, this is because each member of this hierarchy is evolutionary PDE. So it has a unique solution. The initial value problem has a unique solution. And because of this, there is a one-one correspondence between solutions of the Kdb hierarchy and the initial data, our ring V. So, let's see some examples. The first example is if the initial data is given by X, it's just the Fx equals X at the all time equals 0 is X. So in this case, our ring, let's just take the ring to be the formal power series of X. And this is what we often do in this way. And according to the Witten-Kontsevich theorem, this unique solution. So here we have X, and we get the this is our unique solution UT. And in this case, the unique solution governs the integrals of the psi class of the moduli space of curves. So this is conjecture by Witten in 1990s, and first proved by Kontsevich the next in 1992. So here the integral is over the Deligne-Manford moduli space of stable algebraic curves of genus G with n distinct marked points, and these psi are the psi J is so it are psi classes of the moduli space. So it's the first Chern class of the cotangent line bundle of this moduli space. So which means the so this cotangent line bundle is the on each point which is a curve of this moduli space, and the fiber is defined as the cotangent space of the curve at the jth mark point. Okay, so this is the first example, and the second example we can consider the case the initial data given by this a rational function of one double pole, and in this case, the corresponding unique solution is called the generalized Gauss-Witten solution, and this was introduced by Alexandrov and also by Du Nobry. They proved that it's a Kdb tau function, and this, I mean, the unique solution will give rise to a Kdb tau function. We will see later. This solution will be denoted by U, okay, U theta. And according to Nobry, in the case that the parameter C equals 1,8, and in this case, this unique solution will govern the integrals of psi classes coupling the Nobry theta class. So here, if we have, here if we have 1/8 x minus 1 square, and this we also get a unique solution, which is this U we denoted by theta 1/8 t, and this solution will govern the integrals of psi classes coupling theta class. So we call this solution the BGW Nobry solution. Okay, and the third example is so if the initial data is given by the Weierstrass P function, also multiply a constant C. This C is an arbitrary given parameter, a constant, and so in this case, it is convenient to set our ring to be the ring generated by Weierstrass P function and P prime G2 G3, the Eisenstein series, and so with this relation. So in this case, the unique solution is gives the modular deformation of the generalized BGW solution. So this is easy to see because this fx starts with c divided by x squared plus dot dot dot. So and in this deformation, the coefficient are modular forms. So so it's a modular, gives a modular deformation. So we call this solution the Lamé solution, and because the corresponding equation of the corresponding wave function later we introduced, it was considered 150 years ago by Lamé, or maybe even more. So however, the geometric meaning of this solution with a generic C is an open question. So the next example is if the initial data is given by the inverse function of the zeroth Bessel function. And in this case, according to Kaufman, Manin, and Zagir, and also to Dubrovin's observation, the corresponding unique solution will govern the V-Peterson volume of MGN bar. And this important observation was used by Zograf and Dubrovin-Zhang to design efficient algorithms for computing the V-Peterson volumes. So there are also other methods for computing the V-Peterson volumes, including Mirzakhani's recursion and derived from dynamical system and Chekhov Anar Ahantang topological recursion. So and from the interval system, so which means using the Kdb hierarchy, the algorithm given by Zograf and Dubrovin-Zhang is very efficient for large n, so a large number of marked points. Okay, so now let's start with the mathematical structure about Kdb hierarchy. So we will denote by A the differential polynomial ring of U. So it means this A is a for simplicity, let's just write it's like UX. So it's a polynomial of UX, UXX, and so on. And so what we call a tau structure is a family of elements in A, such that it satisfies the following properties. First, the omega 00 is U, and the second, omega PQ is and equals omega QP is symmetric. And the third is that the derivative of omega PQ is also totally symmetric. So, and this is called the tau structure, and the existence and uniqueness is it was known, and if we have a tau structure, we can define the higher what we call correlation functions. So the definition is very simple. You have the tau structure and you just differentiate with respect to Kdv times, and you get to this multi-point correlation functions. And the tau structure itself are 2-point correlation functions. So because of this commutativity of the Kdv flows, these multi-point correlation functions, they are also totally symmetric with respect to their indices. So, and we can get the first few omegas. So of course, the first one is omega 00 is just u, and the next ones you can solve just using the definition of the Kdb hierarchy. It's easy to find and also the definition is easy to find the first few. Okay, so the next idea is about the tau function. So if U is sorry, so if U is an arbitrary solution of the Kdb hierarchy, and from the tau structure we know that. So you see here, since these omegas are polynomials of U, Ux, and so on. So for any solution, you can substitute this solution to this polynomial, and you get you will get an element in this ring, right? After the substitution. And then in this formal power series ring, because of this, we know that the existence of a function tau such that this omega becomes the second order derivatives of log tau. So, and this is the definition of the tau function of the solution. Okay, for our arbitrary solution, we get a tau function. And of course, this definition, the tau function, so although we call it it is determined up to the solution by a linear function. It means adding an arbitrary linear function of the times to the log tau. We will consider them as the same tau function. Okay, and the multi-point correlation functions have also a better and a simpler meaning. So it just becomes the multi derivatives of log tau. Okay, and the next observation is very simple. So since by definition here omega 00 is u. So and this is our familiar u equals dx squared log tau. Okay. And then the multi-derivatives of u, according to our notation, is just omega 00 and p1 to pn. And this means that if we could compute all the differential polynomials omega, then the initial value problem is solved, right? So what is more is that so here we only use omega 00. So and all of these omegas actually gives all the multi-derivatives of log tau. So it means we can also compute if we have all the multi-point correlation functions, then we know tau, we know log tau. So previously I said the partial goal of our study is to compute the initial to solve the initial value problem of the Kdb hierarchy. And actually, the main goal, the actual goal, is to compute log tau. Okay, so of course, if we compute log tau, as the simple observation says, we just solved the initial value problem. So to do this, let's consider the matrix Flux form of the Kdb hierarchy. So we introduce this. Lambda, the 2x2 matrix, 0, 1, lambda 0, and the lambda is a parameter, and Q is 0, 0 minus 2U 0. So, and of course, this is the lambda plus Q is an element in the SL2C. So for the 2x2 matrices, we introduced a gradation of this for this 2x2 matrix. I mean, this SL2C valued formal Laurent series of lambda inverse. And so the gradation is given by we assign degree to this 0, 1, 0, 0, 1. And so the lower triangular matrix, this 0, 0, 1, 0 degree is minus 1, and degree of lambda is 2. And all of these elements in the different polynomial ring is given degree 0. Of course, this condition sometimes it can be for different different applications. You can also assign degree to U. Okay, so and for us at present, it's just this simple principal gradation. So and we define the matrix resolvent associated to the matrix Flux operator L as the unique element, such that it satisfies the following 3 conditions, actually 4, because we also give the space where it belongs to, and also the first condition is R is the bracket between R and L is 0, and then the second is the we can consider as the initial condition is at lambda near infinity, R lambda is start with lambda, okay, capital lambda, and the third condition is trace of R square equals to lambda, okay. So here this initial condition at around lambda equals infinity. So here the rest terms means lower order terms with respect to the principal gradation. So the definition of matrix resolvent and its application to constructing integral hierarchy, actually this was used a long time ago by in systems. So however, what we will do is to consider tau structure. And we want to show that actually all the endpoint generating series of omega, so all these multi-point correlation functions, they can be obtained by this simple object R in an algebraic way. Okay, so let's see. So and this algebraic way is just given by this proposition. So which means so for any n bigger than or equal to 2, because of course the tau structure is defined for any for starting from 2-point correlation functions. So for any n is bigger than or equal to 2, the generating series of these multi-point correlation functions, they can be obtained by algebraic manipulations of this matrix resolvent R. Okay, you just do the multiplication and take the trace. Okay, and these are the generating functions. So here the summation is over the symmetry group quotient the cyclic group. So and also this for an element in the symmetry group, we consider this sigma n plus 1 is sigma 1. Okay, so it gives the permutations. So 1 to n and sigma 1, sigma n. So summation all over the permutations, and so let's first prove this proposition. So the first thing is, since our matrix resolvent is in SL2C, right? So here because our S is SL2C, and the matrix resolvent is in SL2C. So let's first write this R as A, B, C minus A. Okay, it's a typical element in SL2C. So of course, in the 0th step of this proof, we need to first prove so whenever to prove identity, we need to first prove that each side, the left-hand side and right-hand side, are meaningful objects. So first, we need to prove what is R? So to prove the existence of and uniqueness of R. So from the defining equations, we find that this ABC, it must satisfy the following 4 equations. Okay, and these 4 equations simply says A and C are determined by B in a very simple way. So, and B itself satisfy a linear equation together with a quadratic equation. So the linear equation, this is of course simply identified with the Leonard-Magritte recursion. And the quadratic equation is simply integrate once. And also from this quadratic equation, it's easy to see the uniqueness. So so we can do the opposite way. So here integrate once and you differentiate to get the linear equation. So from the quadratic equation you get uniqueness, and then the compatibility gives the uniqueness, which is just to differentiate this quadratic equation you get. So here is the second order equation. Here is the third order. So you differentiate once, and then you get this Leonard-Magritte recursion. And so here, if we the importance of this quadratic equation is that in Leonard-Magritte recursion, you need each time you need to integrate once to in the recursive procedure, and then there are some arbitrary constants of the choice. So this quadratic equation gives the unique choices that the zero constant of the integration. So it's yeah. So it's also quite a geometrical condition. Okay. So this existence and uniqueness follows. So now in the first step we will use so first we will give an alternative formula for the matrix resolvent. So according to Victor Katz and Kosten, this vector space S has the decomposition, so it can be decomposed to, because this lambda is the cyclic element and satisfy the condition in constant condition, and so this vector space S can be decomposed to the kernel of AD lambda direct sum with image of AD lambda. And there's also an orthogonal decomposition, and with respect to Cardan-Killing form, the orthogonality. So and the kernel is also described by Kosten and Katz, and in particular by Katz. So this kernel is given the linear combination of this lambda k, and the k must be an odd number, and which is simply our lambda 0 and times lambda to the power L. Okay, and so the fundamental lemma of Drinfeld-Sokolov says there exists a unique pair U and H such that U is in the capital U is in the image of AD lambda, and with the principal degree strictly smaller than 0, and the H is in the kernel of AD lambda, and also the degree is smaller than 0. So such that this action of EADU on L is given by this dx plus lambda plus H. So since it's I mean the proof is given simply by mathematical induction. So we just omitting this proof. So and then it's already, this is given by Drinfeld-Sokolov. they prove that the matrix resolvent can have this alternative form. Okay, so the proof is also easy because first we simply since we already proved the existence the existence and uniqueness of this in this definition, so you can simply let's just do a u on this the first equation, and you find that this r, if we define r by e to the adu lambda, and then this L satisfies the first equation. And it's also because the degree of u is smaller than 0, and you can prove that it satisfies this initial condition at the lambda goes to infinity. And finally, this condition is also simply because lambda equals to lambda. Okay, and then you use the invariance of this action for the Gadang killing form. So the proof is very easy. So then we also omitted this the details, and so this gives the first step. In the second step, one can express the Kdb flows in terms of the matrix resolvent. So let's introduce this a family of 2x2 matrices Vk. Okay, it's just take the positive part, the polynomial part of lambda to the k times r, and with correction. Okay, and then the Kdb flows can be written equivalent in this form. Okay, and this is also widely used in the literature. For example, in BBT's book and the DK or the body. Okay, and now let's introduce PK, which is given by this exponential of ADU on this all the number, all the elements of this kernel of AD lambda. Okay, so this lambda 1 plus 2k equals lambda k. So it's belongs to the kernel, and this is more or less obvious because of course lambda k capital lambda equals 0. Okay, so this is the D bracket. So in particular, we see that this in this definition, P0 is just our matrix resolvent. So then from this equivalent form of the Kdb flows, you can find the evolution of PL is given by the D bracket between Vk and PL. Okay, so then since we want to consider all the multi-point correlation functions, let's introduce a generating series of the flows of the derivatives with respect to times, and then using this lemma, this equality, and substitute to this generating function, you can get this this lemma in the generating function form. Okay, so the proofs are also very simple. It's a trick. So whenever you see a polynomial part of some low-long series, you can generating series of polynomial part of a low-long series. You can always make it to yeah, so here is, and also here that there's the commutator. So you can always make it to a Cauchy integral. And then there's also some correction terms, and you collect all the correction terms, you get B lambda. Okay, so these correction terms are very important. So this finishes the second step. So we express the matrix resolvent as the we gave a new alternative form of this matrix resolvent, and also we give the evolution of the matrix resolvent with respect to any time. and also the generating series. Okay, then, so in the third step, so now let's focus on the real proof. So for this, first we also need to so now we look at the identity that we want to prove. And this identity, we have already explained the left-hand side, the existence of uniqueness, but we didn't give the proof for the left-hand side, the existence and uniqueness of the correlation tau structure. Let's just assume it is true. And the right-hand side, we have given the existence of uniqueness of R. And to prove the identity, we also need to show the two sides are consistent to each other. So the left-hand side, they are power series of lambda inverse. And the right-hand side, it looks there are poles along the diagonals. So we need to prove actually all the poles in the right-hand side cancel, such that it becomes a form power series of lambda inverse. So for this, we do a trick. This trick seems can be found from Newton. So for any low-long series, you can find this is always it's a true identity always. So it seems used by Newton already. So if we substitute this identity in the right-hand side, okay, and after simplification, we get these terms. So this term will cancel with the first term because trace of lambda square equals 2 lambda. If you differentiate and you use the invariance of the trace AB equals trace BA, you get trace of R prime equals 1. No, equals sorry, equals 1. Yeah. So it cancels with the first term together with the last term. Yeah. So if you combine the first term with the second term and the last term, they cancel. So the only remaining term is this one. And this one, it indeed belongs to the formal power series ring of lambda inverse. Okay. So yeah. So sorry, I think this is not very so it's simply I think. Okay, so let us now denote the right hand side, the coefficients of the right hand side as later omega pq, and by residual computation you can find omega 00 is u. And it's obviously symmetric because it's I'll not go back to the, so it's obviously symmetric. So sorry, we have omega equals omega. So because the trace R lambda, R mu equals R mu R lambda. Now we apply our generating series of the derivatives to the right hand side. We get the, after some computation, it turns out that the Q disappeared. So this, although it's important to describe the flow, in the tau structure, to get the tau structure, this Q, the contribution of Q is 0. So then you only get this, and this is also totally symmetric in permutations of lambda mu nu. So this gives the tau symmetry, the condition of the tau structure. So actually in this proof, previously I said we didn't give the existence and uniqueness of the left-hand side, and now we give, because we gave the existence and the uniqueness. It can be done by some further arguments. So finally, to prove the formula for arbitrary n bigger than or equal to 3 it can be done by mathematical induction. So we just omit the details. So now let's go to the wave function. So I will, be quick because now the object I think is more familiar to us. And so here, let's consider an arbitrary element in the ring V. And we look at this initial Lux operator, which is given by dx squared plus 2f. This is the initial Lux operator. So, and for wave function, it's just this L psi equals z squared psi, the eigenfunction for the Lux operator. And we consider in this space. So, in particular, this psi have this form, okay? So the dual wave function will be defined also as an element satisfying this linear Schrödinger equation, but now it is an element in this space, okay? So it has similarly to the wave function, it has this form. Because these are, I think, very the standard objects in the system, so we just do it quickly. And however, we will define the dual wave function associated with psi. In this sense, it is defined with a further condition, this dx to the power, so all of the derivatives with respect to x, all the higher order derivatives of x of psi times psi star has residue 0 at z equals infinity. And this psi and psi star will be called a pair of wave functions. And it's easy to see that for a given initial data f, the pair, so the psi is defined up to a multiplication by an element in this four power series of z inverse, and psi. So we can multiply. So we can multiply g z to psi to get psi tilde. And the corresponding psi tilde star will be psi star divided by gz. Okay, so this gives the freedom of the pair. So for still for the excuse me, here's for the time dependent case. So for the time dependent case, when the wave function also is evolute with the time, so which gives by psi tk equals L to the power 2k plus 1 L. L to the power 2k plus 1 psi. So, and the evolution of the wave function and the dual wave function together, the pair is also well defined. So, and so let's for a wave function, we denote for the time dependent wave function, we denote the d to be this function. And in particular, if we take t equals 0, we get the time independent capital D. So our first theorem says the generating series of all the multi-point correlation functions can be obtained in terms of this D, capital D. Okay, and the sum is similarly as before, but now it's capital D is a scalar function. But it's a scalar function with depend on two independent variables. So let's see, previously we mentioned the freedom of the pair. And so we can multiply an arbitrary four power series GZ with constant coefficient to psi, and also divide this GZ to psi star. This effect will give a different capital D tilde. However, since here is a GZ divided by GW, the change, and then here is a second. So it's you have D Z sigma 1, Z sigma 2, and so on to D sigma 1, sigma n, sigma 1. So then this factor they cancel in each product. Okay, so gives this because for a given solution U, we know that the left-hand side, our differential polynomials of U is uniquely determined by U. So but the right-hand side is given by the wave function, and wave function has this freedom, so it's not unique. However, the D is not unique, but the product is unique. So it's a remark. And the second remark, I will just quickly. So here is that in this it's very long. I just briefly. So in this identity, you can take time, all higher time equals 0, and then the remark simply says the right-hand side becomes the multi-point correlation functions evaluated at t equals 0. And the right-hand side is also the wave function evaluated at time equals 0. And so this surviving capital D is just can just be obtained by the time-independent wave function. Okay, so this is important because in another approach called inverse scattering for the also use wave function to solve the initial value problem. This approach, this inverse scattering approach, needs a further evolution in wave function, and also the inverse. So you need this solve Gelfand the Left-Marchenko equation to get something, to get the final solution of the initial value problem. But in our solution of the initial value problem, is you only need to compute the initial linear Schrodinger equation, and you get the solution without doing this. So the time evolution in the wave function space, in spectral space, is needed, but it's not used in our formula of the solution. So yeah, okay. So for short, we only need to solve the initial linear Schrodinger equation, and but of course the proof we need the evolution in time. So there's always time, and so for the proof, we first define a matrix. We get together this psi star and psi x star x, and the first statement is determinant of capital Psi equal to Z, and the product of psi star is B. It is our generating series of the Hamiltonian densities, which is given by this Lambda-Marguerite recursion. And this, so now we give the third form of the matrix resolvent is that given by psi times Z minus Z psi inverse. So the proof is also very standard. So here it's a very standard proof. So first we prove this determinant is indeed 2Z. And to see this, it's easy to see the W, all the derivatives of W with respect to the times are 0. So it means this W can only have this form with this SK are constants, pure constants. And so now we prove all these SK are 0. So by computing the residue, okay? And yeah, so these are very standard proof. Maybe I just omit the proofs. And so for proof B equals psi star, similar as before, since we always prove the existence and uniqueness, you simply need to prove psi star satisfy the determinant equation for B. Okay. So now using this lemma, we can rewrite the fourth form of the matrix resolvent is given in this form. Okay, and then we compute the trace. So Z square is our lambda, and we compute the trace of our lambda, our mu. Then the right hand side is given in this form and divide by lambda z1 square minus z2 square. And after the divide by this, we get the formula for n equals 2. And for higher n, again, it's easy to see by induction. The only thing is that you need to prove this identity matrix. Here Z means Z. This identity matrix gives also zero contribution to the sum. Okay. So now let's introduce another function of two variables. Yeah, we can say it's like a kernel. So another kernel is K, capital K. And in this case, this kernel is given only use our B. B is the generating series of the Hamiltonian densities of the KDVs. So these are different polynomials, and that's why the random macro recursion. And it turns out that the generating series of these omegas can also be expressed in terms of K. Okay. And in this cases, I would say it's quite unexpected because it's locality. So here's locality. Of course, the left-hand side is local. The right-hand side should also be local. But from some point of view, from random matrices, usually people suspect that this the kernel should be non-local. But here we get a local kernel. And this seems never appeared in the literature, and also we don't know anything about K. So it's geometric meaning is open. So the proof is also very simple. So it's just that we have these relations psi equals psi star equals B, and psi and this determinant equals to Z. And then the second is just to differentiate with respect to the first equation, and you get the third equation. And from this equation, you can eliminate psi star, psi x, and psi x star, psi star x, and then all in terms of psi. So you see, from this, you solve in this way. There's always non-local objects, right? Psi. However, again, as what we explained about this freedom of this GZ, little GZ is similar that all these psi in these products in these products. So sorry, in these products. In these products, all the psi, all the psi they cancel. So you only get something purely local. Okay, so this finished the proof of theorem 2. And let's go back to our example. The first example is the fx equals x. And in this example, you solve the matrix resolvent and so on. You get the corollary is that the generating series of psi class integrals equals to the right-hand side with the explicit matrix M given here. So here we know that since it's summation over G, so it's an all genera formula, and so because of this, one can consider certain large genus asymptotic of the intersection numbers of certain type. Okay. So, and the next thing is we do, let's see the application of theorem 1. So in this case, the wave function is known and is given in this explicit expression, the wave function and field wave function. So explicit expression for the kernel capital D was obtained by Jian Zhou, and later we gave with Balao, we gave a different proof of a formula for capital DZ. It's very long, so I didn't write here. Yeah. So let's now see the second example. This example is about this Nobri class. Okay, so it's for C equals 1/8 case, we mainly consider this case. So in this case, the generating series of this psi class with coupling Nobri class equals to this, and now the M becomes this matrix. Okay, so it's and again, you can do large genus asymptotes of certain theta class intersection numbers, because the formula is in all genera. So for arbitrary C, instead of C equals 1, 8, we consider arbitrary C. You can also get this, sorry, this is R. So this is R, because we always use R, so it's R. Okay, for the general C, this R is given in this by the hypergeometric 3F0, and so this is also was also independently given by Marco Bertola and Giulio Ruzza. So here also with Bertola and Ruzza, they gave a different proof of this formula, this identity by isomorphism approach. So which gives a different proof, and together with matrix loading. So, and our proof is only use KDB. Okay, so yeah. So the next thing is about this application of theorem 1 in this BGW Nobbery story. And in this case, we have the explicit form of the wave function given by this, and precise star given, you just change z to minus z, okay? And you get precise star. And so we get the generating series of this generalized BGW correlators in all genera. And also we have this explicit expression of D. Okay, so for the Witten-Kontsevich case, we didn't give D because it was already given by Jianzhou. And in this case, we gave the explicit computation for D. It's given in this 3 equivalent expression.
Sorry to interrupt.
Yeah.
This is Nalini. I'm just reminding you that there's only 4 minutes left. And
oh yeah. Thank you. Yeah, I'm almost at the end.
Thank you.
Yeah, thank you. So sorry. yeah. So solving this Schrödinger linear Schrödinger equation to get psi and precise star is easy. And let's just prove how to get this D. So the first thing is that we can find precise star. We gave a linear system of this is given by this ODE system, and then we find the generating series of this AMN, but with this difference, we can solve this generating series of this with my A and B here, and we can do the generation series of A and AN is also given by this. And we can show that the right-hand side and left-hand side, they are equal. They both equal to this. So this proves the recursion for A and N. And then to solve the recursion, we get the closed formula for this and this. And for the last formula, we simply consider as a function, rational function of alpha. And to analyze the poles and all of the poles and compute the residues. So here is the finite sum. Yeah, so by this partial fraction decomposition, you get the last formula. So finally, let's look at the third example of Lamé case. In this case, we do not know a closed formula for psi star for this case. However, for the particular case, if C equals minus of this triangular number, and if particular with P equals 1, 2, 3, we also have the explicit formula of P's. So yeah, so I'll stop here. Thank you.
Thank you very much.
Okay. Thank you, Yang. Is any questions? So maybe, oh, wait a moment. I have questions. So just for the Lamé function case, do you have any explicit formula for the tau function?
Of tau function.
Yeah.
So this way so here for us to get the explicit formula, it means we can give all the multi-point derivative of log tau, and only for this p equals 1, 2, 3 case we have this closed formula, which is given here. So these are the spectral curves.
How does the tau, how is the tau related to the Kdb hierarchy? Do you have any, the dispersion relation?
What version?
Dispersion relation. I mean,
a dispersionist version.
No, not the tau, the t, time. Is it time independent or time dependent?
A tau is time dependent. It depends on infinite many times.
And what's that relation? What's the coefficient in front of that t?
Yes, the coefficient. So there is a Sato theory says that the coefficients of tau, if you change of the basis to the sure polynomial basis, the coefficient will be certain determinant of the of the so-called the determinant so-called molecular coordinates. But in our study, you see the point is that we consider log tau. So for us, the important thing is log tau. The coefficient of log tau in different maybe I didn't mention. So here I can mention here. So there is indeed a meaning. So here, if you consider the inverse of the Bessel function, and you get V Peterson volumes. More or less speaking, if you consider an arbitrary solution of Kdb in some very general setup, in this case, you get generalized V Peterson volumes. This is also due to Kaufman-Manin-Zaghir. So the log tau, so the answer is that the log tau of the times, the coefficient of times in the log tau are also given some intersection numbers, which are called generalized V Peterson volumes.
Okay, now one more question is that I remember that in the third example 3, and you mentioned that there is an open question. What's that? The Lamé case, yeah, Lamé function case.
I mentioned open.
Yeah. So at the beginning you give 4 examples, and the third example is Lamé function.
Okay, I see. Yeah. So in the case, so yeah, you're right. So here, so if c equals 1/8, so the shift of x to x minus 1 is the, I mean, so for c equals 1/8 it corresponds to Nobbery. And the question is that if there exists certain cohomology class such that the deformation of this 1/8 over x square, this deformation also have a certain cohomology class such that the integral is governed by this solution. So yeah.
Okay.
Yeah. So I also saw there is in the chat that there's also a question, right? Sorry, it's a private. So, but I can answer. So there's a question. What's the meaning of this? So some people ask, this governance means what? Where is it written? So this means, yes. So this means these integrals are actually the coefficients of log tau. Is actually what Professor Zhang just asked. So these coefficients are precisely the coefficient of log tau. So P, N, and factorial. This sum equals log tau. And governance means, since the log tau, what we said, the tau can be determined, almost uniquely determined by U, by the solution. So you just consider this initial value problem and you solve U. And log tau is determined by this up to only a linear function of t, which is not very important.
So perhaps I can just step in and remark before everybody has to leave that our next APIOS talk will be on the 6th of April, and it will be given by Dr. Li Shihao on condensation algorithm for Pfaffians and discrete integrable systems.
Okay. So Nalini, so if no more questions, maybe we can close this session.
Yes, thank you.
Okay.
I think so. Thank you so much, everyone, for participating. And thank you very much, Professor Young, for your lovely talk, which covered a very large range of deep mathematics. And I wanted to ask you a question, but maybe I will send it to you by email. Thank you very much.
Thank you. Thank you.
Everyone, bye-bye.
Thank you. Bye.
Thank you.